go to the next talk by Anthony Stefano, looking at evaluation of WRF microphysics using polarimetric data. Anthony?
Thank you so much, everyone. Welcome to my talk and to the session. I'm happy to be communicating with all of you on the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh First Nations, on whose land this talk is made possible. And I also want to acknowledge all of my collaborators and sponsors, of which there are many. This is a very collaborative research effort that I'm working on, and I'm very, very excited to be sharing with all of you what it is that I do, having to do with evaluating WRF microphysics schemes during atmospheric river events in particular, using polarimetric radar data. There is a need, as we all know, to better predict extreme precipitation. Significant precipitation events are common in southern BC and the nearby US Pacific Northwest each year in winter. Numerical weather prediction models can be optimized to better predict these events using reliable observations to validate model equations and outcomes. As we can imagine, this is sometimes easier in some places than in others. In the United States, for example, where there are many, many kinds of observation sources operational at once, there are many different ways to talk about how a weather model is performing. Here in Canada, given the complex terrain, particularly in Southwest BC, but also in other areas of the country, that's not always possible. So we want to think about other kinds of observation sources, particularly and ideally spatially, that we could use to assess weather forecast model performance. Polarimetric radars have become integral for frequently observing clouds and precipitation at high resolutions. Many scientists have begun exploiting data from North America's high-density radar network to enhance microphysics schemes in NWP models, and these simulate the evolution of tiny water droplets into clouds and precipitation. The guiding questions, therefore, of my research are two. First, how frequently do accurate extreme precipitation forecasts correspond to accurate microphysics simulations? For most purposes, and practically speaking, people might be satisfied with a very high performing extreme precipitation forecast for, like, let's say, an atmospheric river event. But we hope in the NWP community that those accurate forecasts are informed by appropriately simulated microphysics parametrizations. And we know from very much literature over time that there are lots of issues that need to be worked on to make these microphysics schemes more accurate. But a second question then is, to what extent can polarimetric radar data be applied as a reliable observation source for microphysical processes? And to answer this question, I came across a very interesting and powerful software package that came out of NASA in the last 5 years, and it's called Polaris. The polarimetric radar retrieval and instrument simulator, also known as Polaris, allows for direct statistical, and I should add, spatial comparison between microphysics scheme output in NWP models and polarimetric radar data. The idea being that we can try and make the left panel, which is an output from a weather forecast model, become more accurate if we inform it based on spatially observed precipitation using radar data. So we use this in somehow to inform how this looks in the end. And this is how Polaris works. It's a basic scheme to explain. Initially, WRF and most NWP output files and netCDFs are not compatible to directly compare with radar observations. The variables are different and the file processing is very different. However, Polaris makes it possible to make this comparison by, in its first component, called Polaris F, converting WRF output into equivalent simulated radar fields. And this is, of course, using the background in radar meteorology and wave theory to convert what we know from weather forecast variables into what we would see if they were radar variables instead. And then these become easily comparable, oranges to oranges. Now, in addition, you can integrate temperature data to help inform the hydrometeor classification and Doppler velocity data to help inform vertical and horizontal velocity fields. And once you have all these together, you can now make this very direct comparison and have some post-processing and statistics computed, which can then allow us to answer the question, as we've been answering over many, many years, why do forecasts differ from observations? And now it's not only in a point sense, but also in a spatial sense. The current study looks at two case studies. One occurred on the 3rd and 4th December of 2015 during the Olympics field campaign, when an intense low pressure system brought rainfall to the Olympic Mountains. Many instruments were deployed to capture this event, and by these I mean things like disdrometers, aerial surveillance, and a whole bunch of other sources, including a WSR-88D polarimetric radar called the KLGX radar, Langley Hill. A more recent study, which all of us can probably remember if we've been watching the news, occurred last year on the 13th to 16th of November, when a similar intense low pressure system brought extreme rainfall to the lower mainland of BC. And in this case, there are few instruments deployed to look at this event, but they did include the CASAG Aldergrove radar. So my idea was I wanted to pull observations from both radars and then run WRF model forecasts for each of these events to recreate them. These WRF forecasts were centered on the radars to be able to directly compare by overlay the radar observations. So on the left, we have the Langley Hill case, where the center is given by the radar, and we have multiple domains extending out from that center. Same thing for the Aldergrove study, where it's centered on the Aldergrove radar, and then we have grids out from there. The innermost radar domain for both is 1 kilometer. Now, if we want to configure these and talk about how these were prepared, for the NWP setups, it's fairly straightforward. We use WRF 4.4.2, informed by initial conditions from the GFF at quarter degree, 931 domain configuration, 400 by 400 cells in the innermost domain centered on the radars. And I looked at 5 different microscheme choices and configurations. These include the WRF single and double moment scheme, the Thomson, the Morrison, and the more recently developed P3 scheme. I studied all 5 simulations, so that combines to a total of approximately 30 simulation runs for this one case and then for the second case as well at Aldergrove. But then to create the Polaris, which ingests the NWP output as well as the observations, I also had to create a configuration for this. And this uses Polaris 4.4 on both stations again. And the simulation data is coming from the innermost domain, so the WRF 1 kilometer. Simulated frequency is the standard, so S-band about 2.85 gigahertz, and coverage up to 300 kilometers. So this is, again, simulated to compare with what the radar is actually seeing for these cases. And now we can look at some preliminary results, which are very exciting. So I'll begin with looking at what the observations look like when we run Polaris, just taking a second to load here. The first panel shows an RHI across the center of the radar station. So this is the type, which should say Y is 0 kilometers. So it's at the level latitude of this is the Aldergrove radar case now. So we're looking at the Aldergrove radar at the cross-section latitude of the radar itself during the most intense period of the Aldergrove, November 2021 case. And the first panel is the hydrometeor classification, as we know, informed by fuzzy logic by all the other panels at the same time. And what we can see is something that we would expect. So we see lots of rain falling to the east of the radar, some drizzle lower behind, a clear melting region indicated by wet snow, that's the WS here. And everything above is under frozen category, so either ice crystal or snow aggregate. We do see some evidence as well of some accretion from low density graupel falling down into regions and then coated by supercooled liquid water to have higher density graupel lower to the surface. But altogether, we see what we expect, including the cone of silence, which is clearly marked. Now, if we want to look at the action region where the melting layer is occurring, so all the things are all frozen or turning into liquid hydrometeors, then we can look at a CAPI at 2 kilometers at that same level. And we can see again a spread in the upper left corner of all the different hydrometeors occurring at that level. So we have things like wet snow, snow aggregates, AG in purple, and we have crystals in the brown here, but mostly wet snow. So we have a clear transition region occurring. Now, most interestingly, if we were to average across the 3-hour interval wherein the storm was at its peak, across all CAPIs in the domain in 1 kilometer, then we can actually get an idea of overall what hydrometeor distribution are we seeing associated with this atmospheric river landfall. And what we see are primarily at low levels, we have drizzle, mostly rain, some high density graupel, a central region in altitude of wet snow indicating a transition layer, and frozen hydrometeors aloft. So the question becomes, do we see this all the time? And if we do, what are our forecasts seeing? Are they seeing the same thing? And if not, Does that suggest something about the microphysics scheme informing that forecast?
2 minutes.
I'm just going to quickly go over the potential because I haven't run yet the forecast version of this. But the potential of Polaris is to have this kind of comparison between the radar observations and what we see for the Morrison scheme, for example. So once converted to an equivalent radar data set, we can actually compare. And what we see are differences. And these differences form the impetus to further look into microphysics schemes and see if making those better can make the forecasts more accurate in the end. And what we see here is a clear, almost missing wet snow layer at 2 and 1 kilometer above the surface. And this is also a different case, I should say. This is for the Langley Hill atmospheric river case. So additional case studies, data from nearby sources, and further optimization of Polaris itself are required to confirm these findings. But if they hold, then so far what I've been seeing is that the melting layer seems to be an area of interest because wet snow is underpredicted by our NWP models, and that's across most of the 5 MP schemes that I've looked at. And there are many next things to do as well. So Polaris does provide a novel approach to visualizing polarimetric radar data and evaluating microphysics schemes as well. But there's more to do. I want to explore looking at a wintertime hydrometeor classification developed at CSU, because it actually includes things like dendrites and other kinds of columns, as opposed to things like hail and big drops, which for these kinds of cases are not really occurring. I want to integrate other velocity data. I want to perform a precip and microphysical verification for both of these cases, which is currently ongoing, and then subset all the data to look at different sections of the storm, prefrontal, postfrontal, to look at how the atmospheric river is performing or what it looks like in different sections. And with that, I give you my thanks and I encourage some questions. Thank you so much for listening.
Thank you very much, Anthony. Questions? We have a question on the chat from Yichen Lo. Do these differences in microphysics, such as the lack of wet snow, impact the total precipitation amount?
I would argue, yes, it does. So there are many pathways in microphysics to get to the output that we see at the surface. So every process really counts. In particular, where wet snow is concerned, we have a lot of melting going on. So the transition from solid to liquid and how much of it is occurring can ultimately lead to how much rain we get at the surface. We would have to account for evaporation going on from on the way down. But generally speaking, yes, that wet snow layer does have an impact on the liquid precipitation that we then measure at the ground.
Do we have any other questions?
I've got a question for you, Anthony. Daniel here. You showed the Langley Hill versus Morrison scheme, and I'm wondering if the Morrison scheme is representative roughly for the other 4 schemes that you looked at, or whether there are any significant differences that you've already observed.
That's a great question. The wet snow missing part, the layer missing wet snow was consistent actually across all of my schemes that I've looked at so far. There were a couple of artifacts that I need to fix because they came from the summer hydrometeor classification routine. And so, like, for example, seeing Graupel above, well above where we would expect it is not physical. But generally speaking, that was a very big eye-popping moment for me to see that consistency. So yes, that one scheme was representative, particularly with the issue of wet snow across that layer.
Thank you very much, Anthony.